Application of two parallel wires with opposite currents. In example, nine point one, we analyzed two parallel wires with opposite currents. Here is what we learned. That if I have a magnetic field of a single wire, that was going to be proportional to 1 over x versus a magnetic field. By the way, that's an infinite wire, not a finite wire. And if I looked at the magnetic field of two wires, and of course it has to be with the opposite currents, then it goes as 1 over x squared. So clearly, a single wire has a stronger field than two wires with opposite currents. Magnetic fields apply magnetic forces to currents in wires. That's what we introduced at the beginning of this lecture. So yes, if you have a magnetic field produced by a wire, it's going to apply a force, and it causes what I'm going to put into one single term, which I'll call signal interference. So this is a catch-all phrase that I'm using. So what do I mean by signal interference? I mean interference, noise, and something else called crosstalk. So it's a catch-all phrase that I'm using, which is not common. So it causes signal interference since electrons are deviated from the path by magnetic forces. Now, It can also induce voltages, but that's really a chapter 10 topic, so I won't go into it here. This signal interference can have major implications on computers and audio cables, since magnetic forces can distort their signals. Maybe I should write that, since magnetic forces can distort their currents slash signals. Now, to reduce this, this interference there are two things that are done. One, the wiring is done so that the incoming and outgoing wires are placed right next to each other. Which reduces the magnetic field outside the wires. So what I'm saying here is that I have this, is that if I have a single wire, what's going to happen is that I can have a wire like this. And let's say that this is the wire that's coming in. So I am having a current that's coming in. And this could be an audio or whatever it is. Okay. Now, what you want to think about is that now, let's say that I have an audio wire. So somewhere in the vicinity of here, there's a second wire. And what's driving this guy here, this is an audio wire. And what you're seeing here is that because that's a single wire, when it applies a magnetic force on this guy, it's going to have a magnetic force because a single wire is larger. It's going to apply an external force that's larger. And therefore, you have a stronger magnetic field acting on this audio cable. So what's likely to happen? It's going to distort the signal. But now if we have two wires, of course, with the opposite direction for the current, I'm now seeing something like this. I have a wire here, and you're putting these guys right next to each other. So in other words, I have the incoming current, and now I have the outgoing current, and it's going like this. So I have a current coming in, and now I have a current going out. Now, because I have two wires next to each other, this audio cable is going to have less distortion. So when I look at this guy, then the field out here is then going to produce a magnetic field that's going to have a smaller external field acting on this. So as a consequence, this audio current is distorted less. And that's just by putting them right next to each other. But there's something else that's really wild. That's so awesome. By twisting wires around each other, there is an additional reduction of B external. And another thing that's also really nice about twisting wires together, it also helps with wire management. It makes wiring just cleaner in your apparatus. So when wires are twisted, together, the magnetic field in adjacent half twists are opposite in direction and cancel some of the field. In fact, it almost cancels all of the fields. I should have been a little bit more careful with that language. But let's see here. Let's imagine that we have no twisting. So then I'm seeing this wire coming here. So here's my red, then here's my gray. So when I'm looking at my currents, I'm seeing that this current is going in that direction, whereas this current is going in this direction. The strongest magnetic field is actually in between the wires, right? This is where I get the fields that add up. So now we're keeping everything really close together. Now what we're going to try to do is we're going to try to do multiple twists. So I hope I can draw this. This is a tricky drawing. So let's see if I can do this. So I'm going to get a twist that goes like this. And then I have another twist here. Let me see if I can get this right. Okay, so if I do this and then I got to continue this process here. And I just want to do a few of these. And I think you're probably, hopefully, starting to see the pattern here. So now let's follow these wires here. So here's my red. And then here's my gray. So now if I follow the current, the red here, which I should probably draw in red, let's say here's my current here, and you could see that this current continues to go this way. Then this current goes like this, then I'm going like that. So now I'm going to follow the other current. If I follow the other current, now look what happens. It's in the opposite here. That's the opposite. That's the opposite. So what you're seeing here is that I'm getting alternating magnetic fields. So if I look in this situation, that magnetic field actually comes out like this. This one goes down like this. So you're starting to see alternating magnetic fields. So in this situation, it would be down, and this one would be down. So if I have alternating magnetic fields and I get more twists, the field essentially cancels out over a distance. So this is with multiple twists. So when I'm looking at this thing, I could say then that more twists give a better cancellation of the external magnetic field. And so what you're finding here is that over the length, the net field, how do I say this? The net field emitted or induced from the current, that is, from the twisted wires is nearly zero. And therefore, any adjacent circuit loop experiences no signal interference. By the way, a lot of times don't call it signal interference. What they do here is they call it an EMI, which stands for electromagnetic magnetic interference. Because the magnetic brings in the electric in this situation. So just as a couple of images, let me show you what I have here. So what typically happens is that you can do it with two wires, and you could see that here I have 4 sets of wires, and you could see that 2 of them are wired, but to really reduce the field even more so, you then take the 4 sets and you twist them, and it actually reduces it even more. And then you could see here is that this is a speaker, and you could see right here, look at that. There's twisted wires, as it should be. Okay, here's the last one that I want to look at is then this is going to be an application of 2 parallel conduct wires, or no, I'm going to call these conductors the conductors, with same currents. And I really love this example. And it has particle physics, and maybe that's the reason why. Particle accelerators like those at CERN use superconducting electromagnets to produce huge magnetic fields, to steer charges along the accelerator. So when we talk about steering protons in this case, we're applying a magnetic force. So what you should imagine here is that imagine that you have a series of magnets. So I'm going to say that here's a magnet here. And I'm not really sure how to draw this, but let's say that this is a magnet right here. And these magnets now are all starting to twist just a little bit. So then I'm going to have a second magnet right here. And then I'll have one more here. And what ends up happening here is that as you do these magnets like this, what you're looking at is that you have a beam pipe. Let's say that this is the beam pipe right here. And the beam pipe carries the proton charges. So this is how you're making them change direction here. You're using these magnets. So what you're finding here is that this is what happens. This is called the beam pipe. And at CERN, what they do here is that they shoot in protons. So now they're shooting in a proton and they produce a current. Even though I didn't say this, I should probably write this. So this is a copper beam pipe that carries the protons. And then this right here is an electromagnet. And typically they're super cooled. And maybe I'll talk about this a little bit more later here. But so when I'm looking at this guy, these are the magnets. And their whole goal here is to produce very large magnetic fields to twist these guys around this arc bend here to steer them. So if I look at this, the way I actually steer them is that these guys have to produce a magnetic field that goes up. So if that's the case here, look what happens. I have a beam of protons coming in, right? So that's going to be my current. I have a magnetic field right here. So then my force then, as we can see here, my force is then going to be in this direction right here. That's going to be my magnetic force. So I'm seeing that this beam is now bending the charges in this direction to keep them in line with the beam pipe. So I'm seeing all of these guys here. And you're seeing here is that this guy here is the magnetic force. And that's what's steering these electrons all the way around. Now, again, they all have magnetic fields that are super huge. And so what I'm going to look at here is that I want to look at one of these electromagnets. So when I look at one of these electromagnets, you're going to see that there's cabling that comes in. And of course, what we're doing here is that we're being very, very careful. We want the current doing what? We want the current coming in, and we want the current coming out. And of course, there's twisting that goes on here. And you can also see here is that there's going to be an enormous magnetic force between these two wires here. So now let's look at what these electromagnets look like. So they're not wires, they're literally cables or conductors, if you want to talk about that. And so the cables of the electromagnets carry current, and look like this. By the way, I also should be careful and say that this is the old cabling, but they look something like that. So there's a combination, and you could see here is that they have a combination of many wires made up of many different of three elements here. And this is all superconducting material here. So if you're looking at this cable, here's what you find. These cables have thicknesses of 4.5 millimeters and run 15,000 amps of current. The only reason they do not burn up instantaneously is because they are super conductors. And conductors tell us that they have resistivity of 0 and sigma equal to infinity, conductivity. And they are supercooled to liquid nitrogen temperatures. I don't remember the temperatures. I know the temperature of liquid nitrogen is 77 Kelvin, but in Celsius, it's got to be somewhere around minus 300 to 350. So I'm just going to say minus 300. That's a Google question. As one might expect, these magnetic fields produced are gigantic. Whew, that came out rough. At 8 Teslas. And there are, if I remember correctly, somewhere around 1,200 of them. And the weight of these guys, check this out. The weight is 35 tons each. Now, we got to be careful here. So these big, gigantic steering magnets, there's not as many as the other ones. CERN probably has 10 to 15,000 magnets, but I'm only focusing on the ones that are steering. Now, when you look at these things, look at that, 15,000 amps. So if I was to, so how do I look at that? Let's look at one detail of the electromagnet. So we have a magnet, and its whole goal is that it wants to steer the beam. So we imagine that we have our copper pipe coming through here. And to run one of these magnets, we have currents that we got to pay attention to. So if I look at the currents, they're huge, right? One of the current coming in is 15,000 amps. Guess what? The current coming out must also be 15,000 amps, that's a lot of current. Now, here's the thing, because they're opposites, we know that they have to have these magnetic forces that are pushing them apart. How big is that magnetic force? So these super large magnetic forces can be estimated by our force relation. So we could then say that the force per unit length is then going to be mu naught I1 I2 divided by 2 pi x. And what you're typically seeing here is that I'm thinking about the force between two cables. Okay. Now note that it's going to change the number here, but we're just trying to get an idea just between two cables. So if these guys are running currents of 15,000 amps, and we know that the diameter of a cable is 4.5 millimeters, it turns out that if you calculate this number, this is about 10 to the fourth newtons per meter, which means it's about 2,300 pounds per meter. Because this is such a large value, a mechanical stress analysis is a crucial part of the design process for the magnets.